Ever wondered how scientists verify that computer-generated data actually mirrors real-world observations? It's a critical challenge, especially with today's massive high-dimensional datasets. Today, we're exploring a groundbreaking study that compares cutting-edge machine learning techniques to tackle this problem. Specifically, a method called the New Physics Learning Machine, NPLM. Let's start with the basics. Generative models are like digital alchemists. They take simple rules and create complex, realistic data. Think of them as AI artists painting synthetic landscapes. But here's the catch: how do you know if their art is accurate? That's where two-sample hypothesis testing comes in. This statistical tool asks, are these two datasets drawn from the same underlying distribution? Imagine comparing two groups of people's heights to determine if they're from the same population. But traditional statistical tests, they struggle with modern data. Think of them as using a ruler to measure a skyscraper. Sure, they'll give an answer, but it's not precise enough. That's where machine learning steps in. By training models to spot patterns, we can push beyond old methods and detect subtle differences that matter. Now let's dive into the NPLM. This isn't your average classifier. It's designed for high-energy physics, where tiny deviations can signal new particles or forces. The idea: use a machine learning model to estimate the ratio of probabilities between two datasets. Picture a detective comparing two crime scenes. Instead of just saying, they're different, the NPLM calculates how different, using a mathematical trick called the likelihood ratio. But here's the twist: training this model takes time. It's like teaching a dog to fetch. Sure, it gets better with practice, but you need to invest effort up front. The study found that while NPLM is super sensitive to subtle differences, its computational cost is higher than simpler methods. Think of it as a high-performance car. It's fast, but it burns more fuel. The researchers tested NPLM against other approaches, even pushing it to handle datasets with 100 dimensions, like analyzing 1,000 features of a single particle collision. They discovered that while NPLM shines in complex scenarios, older methods still have their place, especially when speed matters. So what's the takeaway? There's no one-size-fits-all solution. Like choosing between a hammer and a screwdriver, the best tool depends on the job. For high-stakes physics experiments, NPLM's precision could be a game-changer. But for quicker analyses, simpler methods might still be king. Now let's shift focus to a complementary study that tested 6 statistical tools under different conditions. Imagine you're trying to solve a puzzle, but the pieces keep changing shape. That's what researchers face when analyzing data, especially when tiny distortions can hide big discoveries. What's a deformation? Think of it as a controlled experiment where data gets twisted, stretched, or shifted, like testing how well a detective spots a fake fingerprint when it's smudged or rotated. The researchers tested these tools across 6 types of deformations, measuring 2 key things: accuracy, using 95% and 99% confidence levels, and speed. The lower the confidence number, the more reliable the result, like a tighter grip on the puzzle pieces. For the microdeformation, the tSKS metric was a star, with super tight confidence levels, just 0.01854. But here's the catch: it took over 500 seconds to compute. Meanwhile, tNPLM was lightning fast at 34 seconds but less precise. It's like choosing between a meticulous detective who takes hours or a quick cop who might miss clues. Then there's the sigma deformation. tSKS was still strong but took over 6,000 seconds, like waiting almost an hour for results. Meanwhile, tFGD was faster but less accurate. It's a classic trade-off: speed versus precision. Here's where it gets wild. The sigma J deformation favored tFGD, which had a near-perfect confidence score of 0.00933. But it still took 600 seconds. Meanwhile, tMMD, a metric we've seen before, struggled here, showing how even trusted tools can have blind spots. And the POW plus deformation. TSW won the day with a 95% confidence of 0.0434, but its 99% confidence was higher, a red flag. This suggests the results were less consistent, maybe because this deformation was extra tricky. Finally, the U deformation was a total wildcard. tMMD was the fastest, but its confidence intervals were wide, like a shaky flashlight in the dark. tNPLM was slower but more precise, proving that sometimes patience pays off. So what's the takeaway? There's no single best tool. The right metric depends on the problem you're facing. If you need speed, pick tNPLM. If accuracy is key, go with tSKS, but be ready to wait. This study isn't just about numbers. It's about making smarter choices in a world full of messy data. Next time you hear about AI generating data, remember, behind the scenes, scientists are rigorously testing whether those digital creations are real enough. And this research is a step forward in making sure the machines we trust are telling the truth. Thanks for watching. If you want to dig deeper into how machine learning shapes modern science, hit subscribe. And let me know in the comments, what other scientific mysteries would you like me to unravel?